Monads are fascinating structures in category theory. They have practical applications. Monads can be used to introduce side effects in functional programming. But monads are also of theoretical interest. They tie together so many other concepts. And when you know about monads and how to find them and how they relate to other structures, it allows you to connect so many interesting concepts in category theory. So in this video, I'm going to start out with a fairly basic introduction of the idea of a monad without assuming very much knowledge about category theory. And then in the second part of the video, I'm going to get into some more kind of abstract matters to do with talking about what monads really are and how monads relate to other important ideas in category theory, like adjoint functors and free categories. I think the best way to start this video is to give a general definition of a monad, which is as simple as possible, in the sense that I'll try and minimize the amount of category theory terminology that one needs to understand to appreciate this way of defining what a monad is. So I'm going to define what a monad is in a sort of nuts and bolts kind of way, and then I'm going to talk about a very simple example. And then after that, we're going to get a bit more sophisticated and climb up to a sort of higher perspective, a way of looking at monads which makes them seem more memorable, more natural, and really try and understand how monads fit in with the menagerie of other kinds of things that are going on in category theory. So okay, let's get into then the definition of a monad. And I'm going to assume throughout this video that you're familiar with the basic ideas of categories, functors, and natural transformations. If you're not, you can look at my early videos in this Category Theory for Beginners course on those topics. So, what is a monad? Well, to have a monad, we need a category. Now, functional programmers would probably be thinking of the category set, but in general, we just need some category C. And then the monad consists of three pieces of information. A functor T, which goes from the category C to itself. Such a functor that goes back to the category itself is sometimes called a Endo functor. And in addition to having a functor, we need these two natural transformations. This one eta, which is called the unit, and this one mu, which is sometimes called multiplication. Now this unit here, this natural transformation, this goes from the identity functor of our category to the functor T. And this other natural transformation mu, the multiplication natural transformation, goes from T after T to T. So let's just remind ourselves what kind of information is encoded in these natural transformations. So since we have this unit natural transformation here, that means that if we pick any object B, we have this arrow which goes from the identity functor operating on B to T operating on B. And that's going to be the bth component of eta, the bth component of this unit. And we know that doing the identity functor on B just gives us B. And so if we're thinking about functional programming, then C would be the category set, and T would be a functor from set to set. And so often we'd be thinking of T as some kind of a way of making containers for data structures. So for example, there's a functor T which makes lists of things. So if B is the set of strings, then T of B might be the set of lists of strings. And then we can see that this bth component here of this unit is going to be giving us a function from strings to lists of strings. So in a sort of rough, intuitive way, we could think of this unit here as giving us a way to sort of wrap this information in B into this kind of container that T represents. And this multiplication mu is also a natural transformation. So again, for any object B, we're going to have this bth component of mu, which is going to go from t after t of b to t of b, like this. And so this picture here shows us all of the information that goes into a monad. We just need to define the category C, the endo functor T, and these two natural transformations, mu and eta. And then all we need is that information satisfies a certain condition. In particular, we just need that these two diagrams commute here for every A. And so what that means is that if we compose the arrows on this path, we get the same result as as if we compose the arrows on this path. And similarly, composing the arrows on these paths will yield the same result. And that's it. That's a full definition of what a monad is. So I'll just very quickly point out an example which should be useful for functional programmers, and then we'll get into another example in a more kind of methodical way. So firstly, let's look at a very common example of a monad, which comes up when you're doing functional programming, but it's also useful generally in mathematics. So in this case, the category C that we're going to be working with is the category set, and the functor T is going to be the list functor. So in this case here, if B is the set of integers, then T of B is going to be the set of lists of integers. And in many cases in functional programming, when we have a sort of functor from set to set like this, we can think of that as giving us something like a container, okay? A way to sort of package our data. So we might start with integers, but we can do this functor which gives us lists of integers. They're kind of structures that contain integers. And we can see that this unit is going to be a function that takes integers to lists of integers. So it's giving us a way to package our data into this container. And in this case, the way that this unit works is it takes an integer, let's say 7 for example, could be any integer, and it just makes that into a list with a single element. So it just takes the input and it just wraps it in a list. And the final piece of information is this multiplication, mu here. So how does that work? Well, it's going to take, in our case, a list of lists of integers. So for example, we might have this one, 3, 2, 1. So you see we have a big list, but inside it we have these other lists. So this is a list of lists. So T is this list functor and B is integers. So T of B is the set of all lists of integers, and this is an element of that set. And this multiplication here is going to take that kind of thing and give us a list of integers. And it basically works by flattening this structure, by deleting these interior brackets here. So the result is just going to be 3, 2, 1. So in this case here, where the category C is set, we can see that this monad consists of some kind of a container described by this endo functor T, some kind of a way to put information into the container described by the unit, and some kind of way to flatten things. When we have data that's in a container, we can change that to become data that's just in a single layer of container. And we require that these diagrams here commute for any object A. Now I think this part of the definition should seem the most mysterious at the moment, because I haven't really motivated these diagrams, said where they come from, etc. And really that's because I'm sort of showing you a kind of under the hood definition of a monad. It's actually easier to understand what a monad is when we've appreciated some of the kind of other mathematical ideas that they relate to, and then you'll see where these diagrams actually come from. Okay, so now we get on to the main example of a monad that I'm going to focus on, and that's called the maybe monad. Now I want to focus on this because it's one of the simplest monads, and so we're going to be able to see a lot of the main ideas play out in detail with this example. So firstly, what is the setup? Well, of course, we need a category C. And again, I want to appeal to the functional programmers, so we might want to think of C as the category set, but we don't have to. What we do need is we need C to have some certain structure. In particular, we want it to have a terminal object that we'll denote as 1, and also it should have all coproducts. And so for any pair of objects A and B, we have another object A plus B. Now, if we're thinking about the category set, so if we want to sort of imagine that C is this category set, well, that meets our conditions. And in that case, the terminal object is just a singleton set. So we can think of it as a set which holds a single element called star. And we can think of coproduct as tagged union. So to take the coproduct of A and B, we take the set A, we tag it. So let's say we put a 1 on the end of each of the elements, and then we take the union of that with the set B, which we'll tag with a 2. Now, in order to really have coproducts, we need more structure. In particular, we want it so that for any pair of objects A and B, there's this object A plus B, and that comes with these injection arrows, I1 and I2, which have the universal property that for any kind of similar setup where we have an object H and some arrow F from A to H and some arrow G from B to H, there's this unique sort of intermediary arrow which makes this whole diagram commute. And we call that arrow F, G in square brackets. It's also called the co-pairing of F and G. Now, the way we can think of this in the category set is that this is just the tagged union of A and B. This I1 here is just injecting the values from A into that set, and this is injecting the values from B into that set. And this co-pairing here, F, G, that acts like the function F on the elements which came from A, and it acts like the function G on the elements that came from B. And that's why this diagram commutes, because just doing F on an element of A is equivalent to injecting that element into A plus B and then doing this co-pairing map upon it, for example. So that's something about the underlying structure. So we'll keep this notion that we might be working in set in the back of our minds, but really we're just going to assume that this category C simply has a terminal object 1 and it has all coproducts. Anyway, how is this maybe monad defined? Well, the key thing is this functor T, and in this case, our functor T, and in this case, for a maybe monad, we can write this functor T like this. We can say it's blank plus 1. So what this means, so here this blank represents what we're operating this functor upon. So in other words, so what that means is if we do our maybe functor T on an object A, then we end up getting A plus 1, which is the coproduct of A and the terminal object. So again, if we're working in the category sets, then what set would this be? Well, it would be the tagged union, where we're tagging A with a 1, and we're doing the union of that with tagging our terminal object with a 2. And if we're assuming that our terminal object is just this singleton set that has a single element star, Well, then this is just going to be the set which just has a single element, which is the pair star comma 2. And so to look at an explicit example, if A is the set x, y, z, then T of A is going to be this set here. It has x, y, and z tagged with 1, but it also has this element star tagged with a 2. So back to the general case then, with a category with coproducts, there's another notion which is going to come in really useful, which is the idea of being able to take the coproduct of arrows. Okay, so the idea here is that if we have an arrow f from A to A dash, and we have an arrow g from B to B dash, then we can form an arrow f plus g from A plus g to A dash plus B dash. And this diagram kind of shows how to do it. If we compose f and this injection here, we get this black arrow, I1 dash after f. Similarly, here we get I2 dash after f. And then if we just take the co-pairing of those two things, that does give us an arrow from A plus B to A dash plus B dash, and that's what we call f plus g. It's this co-pairing here. And if you think about what this means in the category set, it just means that we form this function f plus g, which is going to act like f if we put an input from A in, but we're going to get the output in A dash plus B dash. So we sort of do the function to get into A dash and then we inject it into A dash plus B dash. And similarly, this function is going to do g on stuff that comes in to the set B, and that's going to give us the corresponding element, and that's going to give us this result in A dash plus B dash. Really, it's going to live on the right hand side. And so now we have these notions under our belt, we can define how T works properly. Let's suppose we have an arrow F from A to B within our category C. Okay, so this might be a function from a set A to a set B, if we're thinking of C as the category set. Now the question is, what happens when we do T on this arrow? And of course the answer is that we're going to have an arrow T of F from T of A to T of B. But in our case, T of A is going to be A coproduct with the terminal object, and similarly T of B is going to be B plus 1. And so in this case, how is T of F defined? Or if you like, how do we lift F under this maybe monad functor? Well, the answer is that T of F here is going to be F plus the identity arrow of the terminal object. Okay, so that makes sense. F is an arrow from A to B, and the identity arrow of the terminal object goes from the terminal object to the terminal object. So co-producting those two arrows gives us something of the proper form. And the way that we can think of this in our set example is that this would be a function, and if our element is coming from A, then we just do f on it and think of the result as being in B plus 1. And if our input comes from a terminal object, so if our input is star, then we just output star. So it's a pretty simple idea. And so to complete the definition then, we just have to say how these two natural transformations work here, this unit and this multiplication. And so the unit, it's a natural transformation, so for every object A, we're going to have a component like this. And so that means we want to have an arrow from A to A plus 1. And there's an obvious kind of choice for an arrow like that, and very often in category theory, the obvious thing that you can think of is the correct answer when you're talking about what kind of arrows you should have in different situations. And in this case here, the answer is that we can use the first injection, okay? So we're just injecting this A here into A plus 1. And in the example where C equals set, this is also very simple. We'd just be thinking, well, this unit thing here is a sort of function. It takes an element from a set A, and it basically gives us back that same element, but we're regarding it as a member of the set A plus 1. So the final thing we need to talk about then is just this multiplication. So how does this work? Well, it's going to go from T of A. So T of A is A plus 1. And then we want to do plus 1 on that. And it needs, so this is the source object of our arrow, and the target object is just going to be A plus 1. So how is this arrow going to work? Well, we want to do a sort of co-pairing, and if we're starting from this plus 1 on the far right, then we want to go to this plus 1 on the far right here, which means doing a second injection. And otherwise, we'll just leave the result unaltered, and we'll get the thing in A plus 1. So in the other case, we'll just do the identity arrow. So hopefully this way of thinking about multiplication is not too confusing. You can see the multiplication arrow here on this picture, which might make things easier to understand. So there's mu A there. Basically, we can see that if we have something from A plus 1, we can just do the identity arrow on it to get something in A plus 1. And if we have something in 1, we can just do the second injection to get something in A plus 1. And if we co-pair those two things together, then we get something from A plus 1 to A plus 1. Now, it's easy to think about what this means when we're working in set. So the usual kind of programming interpretation of this maybe monad is that you think of this element from this terminal object, this plus 1 thing that we put on the end, as representing an error, okay? So you could have a function f from A to B, and that's fine. You put in any element of A, and an f of A is an element of B. That's fine. But maybe you want to think of a situation where that function could go wrong. So then we could think of a function which goes from A to B plus 1. So the function might give you a value of B, but it could also give you this kind of star as the output value. And that star as the output value, which might happen because one, we're thinking of it as this set which just has a single element that we call star. And if star is the output value, we think of that as meaning an error, okay? So for example, maybe A and B could be the set of real numbers, and R might be the square rooting function. And if you try and square root 16, that's fine, you get 4. If you try and square root a non-negative real number, you get another real number, and that's fine. But what about if you try and square root -1, for example? You get an error because that's not a real number. So the way we could model that is to say that in that case, the output would be star. Okay, so the square root of -1 is star in this setup. And so if we're thinking about this set theory case, then we can think of A plus 1 as the set of values of A with this extra sort of error value possibility. And then the way we can think of A plus 1 is that it's a set which has entries which are either values of A or kind of type 1 errors or type 2 errors. And then the way that this mu works is that if we started with a value of A, we just get that same value of A back. But if we started with an error, either a type 1 error or a type 2 error, we just end up with an error, because A plus 1 only has one kind of error, star, whereas this would have these sort of two different possible kinds of errors. And so that's basically what the maybe monad is. And what it allows us to do is it allows us to take the ordinary happenings of our category C that we might want to be doing functional programming in or something, and then kind of move to another world where there are these possible sort of side effects, where in the functional case, our functions might be outputting errors. Or another way you can think of this is that it allows us to deal with partial functions, because a partial function, ordinarily a function is, ordinarily in a function, we define an output for every input, but a partial function might only be defined for some inputs, and for other inputs, we don't really have a definition of how it works. And we could model that by saying, well, there's this extra kind of star value, the kind of error value, and we sort of model the places where our function is not properly defined by saying that when we have such a value, we're just going to send it to this kind of error output. Okay, so we know now what monads are, and the question is, what are they good for? And it turns out that you can do a lot of different things with monads, but I'll carry on just initially focusing on this functional programming story. So if you're doing functional programming, basically monads allow you to do similar kind of programming with side effects. Okay, so the way that this is achieved is formalized with this idea of a Clysley category. So the basic idea is that normally when you're doing functional programming, you're composing functions. So you have something like an arrow f from A to B, and then you compose that with a arrow g from B to C, and those would be functions, and you're composing functions, and so on. But if you want to have side effects, you might want to say, well, actually, I want it so that my function, yes, I put in a value of type A and it gives me a value of type B, but I want it to do something else as well. I want it to maybe break when it encounters an error, or I want it to record some kind of string, or I want it to make some kind of output appear on the screen, or, there's all different things that you might want to do. And a lot of these happenings can be modeled using monads. And if you find the appropriate monad to model the side effect you're interested in, and you look at the Clysley category for that monad, that can give you a way to model these kind of mappings with side effects. And basically the idea is that we'd think of our monad T as some kind of a container, and somehow what working in the Clysley category allows you to do is to think about arrows which are of the form which go from A to T of B. Okay, so now this function f, it doesn't just go from set A to set B, it goes from set A to T of B. So remember, if we think of T as some kind of a container, or a sort of embellishment of the type B, then having a function of this kind of form is sort of richer, right? Because in addition to maybe giving us some values of type B, it might be giving us some other stuff, or it might be returning multiple values of type B or whatever, depending on the nature of this functor T. And the really clever thing about Clysley categories is they allow you to compose these, is that Clysley categories allow you to actually compose arrows of this kind of form. Arrows which go into these sort of wrapped data structures. So I think the easiest way for Clysley categories is just to show you the definition, and then we'll go through this example with the maybe monad. And then when we look back, I think the idea will look a lot clearer. So let me now define what the Clysley category is. So we have our category C, and we have our monad. So we have T, we have eta, and we have mu. And with that information, we can define the Clysley category of T. And this is, of course, a category. So we just have to ask the basic questions. What are the objects? What are the arrows? How does composition work? What is the identity arrows? So let's answer those questions. Firstly, what are the objects of the Clysley category of T? And that's easy because the Clysley category of T has the same objects as the original category C has. Okay, so for example, if C is set, then the objects of this Clysley category are again just going to be sets. Now the big question is, what are the arrows of the Clysley category of T? And so when we have an arrow from A to B in this Clysley category, I like to use a bit of different notation for it. So I do an arrow with a dot in the middle of it from A to B, just to remind me that this is an arrow in the Clysley category that goes from A to B. And this will correspond with a certain kind of arrow in our original category C. Okay, so we can think of an arrow from A to B in the Clysley category as corresponding to an arrow in the original category that goes from A to T of B. Okay, so basically when we have an arrow from A to B in the Clysley category, we can think of it as sort of representing like an arrow in the original category which goes not to B but goes to T of B. So basically it's almost like an arrow in the Clysley category is like an arrow in the ordinary category with possible side effects, if that makes sense. But then that begs the question, how on earth are we going to compose arrows in the Clysley category? I mean, look at this picture. We have a Clysley arrow from A to B and a Clysley arrow from B to C. So those are going to be corresponding if we look at things through the perspective of the original category. If we look at things as they are in the original category, that means we have an arrow F from A to T of B, and we have an arrow G from B to T of C. So how on earth are we supposed to compose those? How are we then supposed to make an arrow that, how are we then supposed to make this composition of these Clysley arrows? I mean, we want to get a Clysley arrow which goes from A to C, which would correspond with a ordinary arrow that goes from A to T of C. But how can we build such a thing given this arrow F from A to T of B and this arrow G from B to T of C? And so actually this commuting diagram here tells us how it is that we can compose arrows in this Clysley category. You see, if we can make, you see what we want to do is to make an arrow from A to T of C in our original category. And we'll call that arrow G star F. And that's going to correspond to the composition of the Clysley arrows G and F. So here's what we do. We start with this arrow F. That goes from A to T of B. And then what we do is we lift this arrow G here, and that gives us this arrow T of G, which goes from T of B to T of C. And then all we have to do is do our multiplication to get back down to T of C. And that's what we want to do. And so this is very cool because it means that we can sort of compose these arrows with side effects. And we'll see very shortly when we look at the example with maybe monads, how useful this kind of thing can be in like practical situations. And so finally, what is an identity arrow in the Clysley category? So that would be a Clysley arrow from A to A, corresponding with an ordinary arrow from A to T of A. And it's just going to be the 8th component of the unit. And so there we have it. That's the definition of a Clysley category. It has the same objects as the category C, but its arrows, like an arrow, but its arrows are a bit different. A Clysley arrow from A to B corresponds to an ordinary arrow from A to T of B. And this is how composition works. And the unit gives us the identity arrows. So the easiest way to really understand what's going on here is to look at a practical example. And so let's look at the Clysley category now of the maybe monad. And so then, what are the objects of this category? Well, they'll be the same as the objects of C. So maybe we could think of C as set. So we could, in that case, the objects of this Clysley category are again just going to be sets. What's a Clysley arrow from A to B correspond to? Well, it's going to correspond to an ordinary arrow from A to T of B, or if you like, from A to B plus 1. And this is the core idea here, because what we're saying here is that an arrow in this Clysley category of the maybe monad corresponds to an ordinary arrow from A to B plus 1. So what does that mean? Well, if we're thinking in the category set, then a function of this kind of form, it's going to take in a value from A, and it might output a value from B, but it also might output an error. Okay, it might output star. It might output the value in this terminal object, this singleton set that we've tacked on to the end of B. And so now we can see that a Clysley arrow from A to B, when we're working with this maybe monad, basically corresponds to a sort of function from A to B, but a function with side effects, a function with the possibility of outputting an error. Or if you like, you can also think of this as a partial function. You could say, well, maybe there are some input values, some values of A, for which f is undefined. And in those cases, when you feed in such an input, f is going to spit out an error. And the really cool thing here is that when you work in this Clysley category of the maybe monad, it gives you a way to compose together these kind of functions which might output error values. So in particular, let's look at this situation. So we have this function f, which goes from A to B plus 1. And we have this function g, which goes from B to C plus 1. And so now how do we compose these together? Well, all we have to do is just look at this diagram and interpret it for the particular monad that we're working with. So T of B, that's going to be B plus 1. T of G, that's going to be G plus the identity of 1. T of C, that's C plus 1 plus 1. And here we've got C plus 1. And this multiplication is going to be ID co-paired with the second injection. So if we have a look at this commuting diagram here, it basically tells us how to compose these arrows for our maybe monad. And actually in this case, with the co-products and whatnot, it turns out that we can really simplify this diagram a bit. And so if you think about the universal properties and whatnot, you can convince yourself that the composition of these two green arrows here is going to be this orange arrow here, which is the co-pairing G, I2. And so basically we could say that the composition of these Clysley arrows, F and G in this case, corresponds to the ordinary arrow where we just do this F here, and then we do this co-pairing of G and I2. And there's a very kind of direct way that we can interpret this, and that's basically to say that when we're working in set, for example, we're going to do this function f, and if it returns a value of b, well then we're just going to do the function g afterwards. But if it returns an error, or star if you like, then we're going to do the second injection and we're going to return an error at the end. So it makes sense, right? If you're imagining composing functions which might return errors and you've got this program and you're going to run it line by line by doing these functions, then as soon as one of those things has returned an error, that means something's gone wrong, and an error should be your final output. And so that error is just going to get passed forwards as you keep composing things within this Clysley category of the maybe monad. And finally, what's an identity arrow of this Clysley category? Well, that's going to be an arrow from A to T of A, and remember, T of A for us now is A plus 1. And in fact, this identity and in fact, this Clysley identity arrow is just going to correspond to the ordinary arrow, which is just going to be the first injection here, I1. And that's it. That's the Clysley category of the maybe monad. So often we'd write such a category as KL of blank plus 1, blank plus 1 being this sort of blank plus 1 being this sort of maybe monad. But another bit of notation which is sometimes used, which is quite telling, is par of C. So sometimes people would call this category the category of partial morphisms or partial arrows of C. Because we're really playing with these arrows that don't go to B, they go to B plus 1. And we can often interpret that as meaning we're really dealing with sort of partial functions or partial maps. And so this Clysley category of the maybe monad can be really useful for thinking about real world things. So here's an example. We could have a function from some set of people to a set of cars, and a function from the set of cars to the set of radios. And so maybe this first function gives the most expensive car owned by, and so maybe this first function, when we operate it on a person, we get the most expensive car that person owns. And then when we operate this second function on a car, we get the radio in the car. However, if you think about the real world, it makes sense to actually think of these as partial functions, right? So actually some people don't own cars. So if Joe doesn't own a car and you do this function here on Joe, then you'll get an error. Okay, and similarly, some cars don't have radios. So if you do this function here on that old Beetle that doesn't have a radio, well, then again, you'll get an error. And you can compose these two arrows in this Clysley category of the maybe monad. And again, if you're operating this on, and then if you operate this composition on somebody who doesn't, and so if you form this composition and then you apply that kind of function to somebody who doesn't have a car, of course you're going to get an error, because you'll get an error here and then it'll get automatically carried along by the sort of machinery of this Clysley category. Okay, so now we know what a monad is. This is a monad, such that these diagrams commute. But I guess you may be asking, yeah, but what is a monad really? Why do we need these diagrams to commute? What's the intuition? What's really going on? And so let's move on to the next part of the video, where we're going to go into things a bit more deeply. So the key idea that we need is the notion of a monoid, because it turns out that in some sense a monad is a special kind of monoid. Now I must say I find it a little unfortunate that monoids and monads have such cryptic names, and also they sound kind of similar, so sometimes things can sound quite confusing, but really the idea of a monoid is very simple. So let's start thinking about a monoid in set, and basically that's just going to be a set of things. In this example, the set where we have these elements 1 and -1, and we have a sort of binary operation which allows us to take a couple of these elements and get a new element. And in this case, our binary operation is multiplication, and we insist that this operation satisfies a couple of special properties that I'll get onto shortly. And so this is a very simple kind of system. We have these two numbers, 1 and -1, and we're thinking about what happens when we multiply them together. Instead of calling this binary operation times, I want to call it dot. And instead of calling this element 1 here, I want to call it I. So I want to call this thing I because it acts like an identity element. And so now we're looking at things this way. I'll give you the definition of a set-based monoid. Okay, so here we are then. This is the general definition of a sort of set-based monoid. Okay, and so what do we have? Well, we have a set S. So in the previous example, S would be this set with two elements, -1 and I. And we have a binary operation. So in the previous example, that would have been multiplication. And we have this special element I, which is like a kind of identity element. And so the fact that this dot thing here gives us a binary operation is specified by saying we have a function. It's called dot, which takes a couple of elements of S and gives us a new element of S. As I say, the identity element is in S. And we also insist that using this multiplication, and we also insist that this binary operation is associative, meaning that this equation always holds, and also that I acts like an identity element, meaning that if we sort of multiply x by I, we always get x back. And so this is the familiar notion of a monoid, but I will say it's a monoid in set, and you'll know what I mean by that shortly. Now, in order to really understand what a monad is, in order to really understand what a monad is from a high level, we want to generalize the idea of a monoid in a certain direction. In particular, we want to sort of categorify the idea of a monoid. So we want to think about some kind of a category, which in some sense is kind of like a monoid. And so what do I mean? Well, the definition is over here on the right. So instead of having a set with a sort of binary operation, instead let's have a category C with a functor, which goes from the product of that category with itself to that category. And instead of just having an element I in this set S, let's have an object, capital I. And then again, we're going to assume that this sort of multiplication operation that we have is sort of associative in the sense that A times B times C is equal to A times B times C, and also that this I here, this capital I, which is often called the monoidal unit, is kind of neutral with respect to multiplications. So timesing an object by I just yields that object back again. And so this sort of circle times functor here is often called tensor product. Is often called tensor product or monoidal product. So we could say that this here is the monoidal product of B and C, and I is often called the monoidal unit. And categories that have this extra kind of structure, that we can define this sort of multiplication-like operation on objects with these properties, those kind of categories are called strict monoidal categories. And I'll explain why we say that they're strict momentarily. But I just want to first point out that this circle times thing here is really a functor. Okay, so that means that in addition to being able to talk about the product of objects, we can also talk about the product of arrows. So if we have an arrow F from A to B, and we have an arrow F dash from A dash to B dash, then we can use our tensor product to give us the arrow F tensor product F dash, which goes from A tensor product A dash to B tensor product B dash. And there we go. That's the basic idea of strict monoidal categories. Now actually we want to go a bit further, and we want to think of a slightly sort of weaker notion, which is just called a monoidal category. We don't want to be so strict about things. In what sense are we relaxing things? Well, the way that we're relaxing things is that we're no longer going to assume that this kind of tensor product thing is exactly associative. It doesn't have to be that A times B times C is exactly equal to A times B times C. Instead, it's enough to say that these things are just isomorphic. And in a similar way, rather than insisting that I times A is exactly equal to A and A times I is exactly equal to A, we're just going to now suppose that those things are isomorphic. And actually we're going to suppose that these kind of isomorphisms are special ones that have particular nice properties. And so this isomorphism from I times A to A, we have a name for it, and we normally call that lambda subscript A. And this other one, we usually call this rho subscript A. And this kind of isomorphism here that gives us something like an associative law, we call that kind of isomorphism alpha ABC. And really these purple arrows I've just drawn come from natural transformations, natural isomorphisms in fact. And we have names for them. Lambda is called the left unitor, rho is called the right unitor, alpha is called the associator, and there's a few little extra conditions that these kind of arrows have to satisfy. Actually, I did a whole video on monoidal categories and symmetric monoidal categories where I cooked apple crumble and talked about wiring diagrams and lots of things. And you might want to check that out because there's a lot to monoidal categories, and understanding them better will really help you to get your mind around the notion of monads more easily. But anyway, this is really the core of what monoidal categories are about. We have a category, we have a way to multiply the arrows and multiply the objects, and we have this kind of monoidal unit, and we have these kind of laws which are basically saying that this kind of multiplication on objects sort of works like a monoid, but not really strictly, just kind of up to isomorphism. Okay, so now we know what a monoidal category is. Let's have a look at an example that's going to be really important for us today, which is going to be set. Okay, so the category set is a monoidal category. The tensor product is just going to be the Cartesian product. So we know how to take the Cartesian product of sets, the Cartesian product of A and B being the set of all pairs with the first element from A and the second element from B. And then our monoidal unit, I, is going to be the singleton set, which we can write as 1. Or we can think of it as the set that just has one element, star. So we know that product can act like a functor, and that's fine. And of course, the singleton set is a set. What about these kind of rules? Well, these make sense, right? So if we have these three sets, then we do indeed have that A times B times C is going to be isomorphic to A times B times C. And this kind of isomorphism here, is really just kind of changing the way that we're bracketing the elements of this kind of triple here. So we'd be changing A comma B comma C to A comma B comma C. And so this is telling us here how our associator natural isomorphism is working. And also we're going to have these unitors here. So we can go from A times 1 to A. And we can do that by sending the element A comma star to the element A. And so that gives us the right unitor, and the left unitor works in a similar way just by dropping the star off on the left hand side. And so hopefully you can see that set can be thought of as a monoidal category. And actually, you know, set's obviously a very important structure, But notice that we do really need to kind of introduce these sort of isomorphisms here to talk about set. I mean, set is not a strict monoidal category because, you know, A times B times C is not strictly equal to A times B times C. They're just isomorphic. And so, yes, this is a monoidal category, but not a strict monoidal category. And so now we have these definitions under our belt. We can move a bit closer to this understanding of the monad. Okay, so now we get to a really key stage in understanding monads. And it's a little bit of a jump because, well, mostly to be honest, because the terminology has mon in it in so many different places, meaning different things. It can get a little confusing. So let's just make sure we're really clear about this. We have just seen that this category set can be thought of as a monoidal category. And we've also looked previously at the idea of a monoid, basically a set with a binary operation that has some special properties. And so now I want to talk about the same thing, this monoid, but I'm going to call it a monoid in set, okay? But it's just the same thing. It's just this set S that has this binary operation dot and this identity element I. The only thing is, now I want to describe this monoid in a more kind of categorical way. In other words, I want to describe it using some arrows and commuting diagrams and things. But I'm just talking about the definition of a monoid in set. And so how are we to think of it? Well, we'll work in the category set. We have this set S, so that's going to be an object of set. We have this binary operation dot. It's a function that takes in a couple of elements and it gives us a new element. So if we feed it the pair x comma y and we do dot, then we get x dot y. And I can also be thought of as a function. It's a function from this singleton set. And it maps the only element star in the singleton set to the element I in S. And what we require, and so this little picture here tells us what goes into a monoid, and then these diagrams here say that the operation, and then this diagram, and then to say that this diagram commutes means that, and then to say that this diagram commutes means that this dot operation is associative, and to say that this diagram commutes means that our element I really acts like an identity element. So let's just follow through this diagram. What's it mean? Well, we have X, Y, and Z here, which are organized like this. We could reorganize them with our associator so that we get X, comma Y, comma Z. We could do the dot on the first element, leave the other element alone. So we get X dot Y, comma Z. And we could dot that. So we get X dot Y dot Z. That's what we get going this way around. Going the other way around, we get X, comma Y dot Z. Now doing dot on that should give us something equal if this diagram commutes. And so we should get that what I've already calculated is equal to X dot Y dot Z. So yes, this diagram here gives us associativity. Okay, so I just made a couple of mistakes with this diagram at the bottom right here, but I've corrected them now. And so if we follow this diagram, let's go to the left here. We start with X, and now we have X comma star. So we've tacked a star onto the right-hand side using our right unitor row here. And now that becomes an I, so we have X comma I. And then we do a dot, so following this path on the left gives us X dot I. And in a similar way, following this path here gives us I dot x, and following this middle path just gives us x. So indeed saying that this diagram commutes means that I really does act like an identity. And so now hopefully you understand that these blue arrows and things are really describing to us what it means to have a monoid in set. And actually I should have written this multiplication here in set just as a times without a circle, because it's just the ordinary Cartesian product here. And so now there's something I want to do with this, which is that I want to basically use exactly the same picture, but now to define what it means to have a monoid more generally in a monoidal category. Okay, so it sounds like a big jump, but it's really very trivial. All we do is take exactly the same definition as we have here, which is written in this kind of categorical way. But instead of just thinking about this as something that's happening in sets, we basically use it as a definition for a monoid more generally in a general monoidal category. And so it's really very easy to do this. To give this sort of definition of what it means for us to have a monoid in a general monoidal category now. So now C is a general category with a monoidal product circle times and a monoidal unit I. Not necessarily a strict monoidal category, but just a monoidal category C. And so all we have to do to define what such a monoid is just turn these times symbols here into circle time symbols. So now we're talking about a tensor product, and the 1 is replaced with an I, which is the monoidal unit. And that's pretty much all we have to do. And so there we are. We've just got the same definition of a monoid that we had before within this category set. And all we've done is just changed our notation a little bit and then said, well, this blue and purple stuff here is now defining what we consider to be a monoid in a monoidal category. So this is actually a huge leap because there are so many different monoidal categories, and now for each of them we have our kind of native version of what a monoid is. So here's a rough analogy for you. You could think of every monoidal category as like a different planet, and then the monoidal category set is like Earth. And the idea of a set-based monoid is kind of like a car. Okay, so we know what it means to have a car on Earth. But then there could be all these other notions of cars that act in different sorts of ways because of different sorts of gravity and conditions on other planets. And that would be analogous to having a sort of monoid which is defined with respect to a different monoidal category. And the really cool thing about understanding what it means to have a monoid generally in a monoidal category is that now we can say what a monad is in a very, very short sentence. Okay, so just before I do that, here we have this idea of a monoid in a category C. Now I just want to change this definition slightly. I just want to call that C D instead. Okay, so that's fine, right? So what I've written here is what I consider to be a monoid in this monoidal category D. And just to reiterate, a monoid in this monoidal category D consists of an object S of D together with an arrow called dot from S tensor product S to S, and another arrow I from capital I, and another arrow I from the monoidal unit to S, such that these two diagrams commute. So here comes the true understanding of what a monad is. Okay, a monad is just a monoid within the monoidal category of Endo functors. So let's go back to our old picture of a monad. So let's go back to our old picture of a monad that we started with. Okay, recall I said that the monad consists of this endo functor T and these two natural transformations. And so this stuff is going on in this category C here. So now let's consider the category of endo functors of C. Okay, so we might write that category as C to the power of C, or actually today I'm going to write it like, today I'm going to write it with square brackets. So I'm going to write it as C, comma C. So what is this category here? So what is this functor category here? Well, it has objects as functor. Well, it has objects corresponding to functors, like T1, that go from C to C. And what about the arrows within this functor category here? Well, they're just going to be natural transformations. So a natural transformation beta from the endo functor T1 to the endo functor T2 corresponds to an arrow beta from the object T1 to the object T2 within this sort of category of endo functors here. So now all we really need to do to gain this kind of mystical monad understanding is just to appreciate how it is that this category of endo functors here, C, C, is a monoidal category. And then we know everything we need to know, because once we understand how this is a monoidal category, we know what it means to have a monoid in a monoidal category, and I've already said that a monad can be considered to be such a monoid within this thing. And so now here we are. Let's see how this category of endo functors, C, C, can be considered to be a monoidal category. So on the left here, I've got the general sorts of structure that we want to know about in a monoidal category. The most important things are the monoidal unit, and that's just going to be an object of D, and the monoidal product, which is this functor. So we need to know how it's defined for objects and how it's defined for arrows. And so on the right here, I'm saying in what respects we can think of C, C as a monoidal category. Okay, so the easiest thing to start with is what's the monoidal unit? And so what we want is an object in this category. So we want a functor from C to C. And what we choose is we choose the identity functor of C, and that's going to act as our monoidal unit. And that's because for our tensor product, we're just going to have functor composition, basically. So the objects of C, C are just going to be functors from C to C. And of course, since these are endo functors, if we have a couple of them, like T1 and T2, then we can form a new functor, T1 after T2. And that's, of course, going to be another endo functor of C. So we have this notion of being able to take the product of objects in this category. But we actually want this, this circle thing here to really give us a monoidal product. So it really has to be like a kind of, so we don't just want to define how this thing works on objects of C, C. We also want to define how it works on arrows of C, C. So what's an arrow of C, C? Well, it's just going to be a natural transformation. So let's suppose now that A and A' are both functors from C to C. So that means that we can think of A and A' as both being objects within this category C, C. And so what's it mean then to have an arrow from A to A' within this category? Well, that just means that we're going to have a natural transformation beta from A to A dash. So we can regard this natural transformation beta in our original category as a sort of arrow within this category of endofunctors. And similarly, we may have an arrow gamma from the object B to the object B dash within this category of endofunctors. And so now the final question is, how are we going to define our kind of tensor product of these two arrows, right? So we have this arrow beta from A to A dash. We have this arrow gamma from B to B dash. And the answer is just horizontal composition of natural transformations. And so if you don't know what that is, you can have a look at my video on natural transformations where I define that. And so now we see the sense in which this category here can be thought of as a monoidal category. It turns out to be a strict monoidal category, and a monad is precisely just a monoid within this kind of category. And so now we're there. We've eaten enough definitions to understand what a monad really is. Because we know the sense in which this category of endofunctors can be considered to be a monoidal category. Now you might be asking, yes, but what about rho and lambda? But what about rho and lambda and alpha? What about those natural isomorphisms? Well, don't worry about those, because this is actually a strict monoidal category. Again, the isomorphisms involved, those unitors and associators, they're just identities in this case. So this is a strict monoidal category. So we really understand what it is. We've already encountered this idea in general of a monoid in a general monoidal category. So now let's consider a monoid. I'll use the same notation for now, S dot I, but in this monoidal category of endofunctors. So the category is the category of endofunctors. The tensor product is this circle thing here, which is basically composition, and our monoidal unit is now the identity arrow of C. So what's a monoid in this category of endofunctors? That is precisely what a monad is. A monad is just a monoid in the category of endofunctors. Now, of course, we like to use some different notation for monads usually. We don't normally write S. We normally call the endofunctor T. So T is an object of this category, C, C. So T is a functor from C to itself, if you like. Instead of writing dot for the kind of multiplication operator, we use mu. And instead of writing I, we use eta. And now you know why it's called the unit, because it acts like a unit. It acts like an identity in a sense. And so now we can make these symbol replacements, and we'll see that we just get the familiar notion of a monad out. Okay, so instead of T's, so instead of S's, we write T. Instead of circle times, we write compose. Instead of dots here, we write mu. Instead of I here, we write eta. Instead of big I, we write the identity functor of C. And so let's carry on. We can do the same kind of thing to our diagrams. So this one here is going to be T after T after T. This is going to be T after T after T. This is going to be mu after identity of T. And there we have it. We've made these substitutions here. So when we've got these composition symbols on arrows here, that means horizontal compositions of natural transformations. And so basically to say that these blue diagrams commute here, well, that's pretty much how we started. Now we know where these diagrams came from, which we started with, because the way I got these diagrams is basically just to look at those diagrams I just showed you and look at those natural transformations and then just look at the kind of eighth component of them. And I thought that was a nice way of sidestepping having to talk about horizontal composition of natural transformations, which is a pretty obtuse concept to begin a video like this with. But really now we see where those diagrams come from, because really those diagrams are just for diagrams which say that this kind of monoid in this category of endo functors has the kind of properties that monoid should have. In particular, its sort of multiplication is associative, and its kind of unit acts like a unit should act. And also the kind of alpha, rho and lambda here are all just identity arrows, because we literally know that T is actually equal to T after the identity arrow of C, and so on. So a monad is a monoid in the category of endofunctors. And so now you know. And also now you know that really the most general concept here is the idea of a monoid. The idea that we can have monoids in different monoidal categories. And we know that monoids in set are very interesting. Now we know that monoids in categories of endofunctors are very interesting. But of course, there's lots of other monoids in other monoidal categories. So if you have a look at my video on monoidal categories, I highlight quite a few interesting examples, and it's really worthwhile to think about what monoids look like in those different categories. So that's the kind of intermediate part of this video done with. Now I want to get on to kind of the advanced stuff. So I viewed what we've gone through so far as something like a description of what monads are, kind of with a focus on helping people who are interested in things like functional programming. But like I was saying at the beginning, pure category theorists are also very interested in monads. And that's because they have deep connections with the ideas of adjoint functors. At least that's one very good reason. So the more you study category theory, I think, the more you like adjoint functors, the more you see adjoint functors appearing in all sorts of places, describing all sorts of concepts. And there's a really deep connection between adjoint functors and monads. So that's what I want to talk about now. So let's suppose we have these adjoint functors. So we have that this functor R is the right adjoint to this functor L. And associated with this adjunction, we have this unit, eta, and this co-unit, epsilon. And if you don't know what I mean by adjoint functors or unit or co-unit, you can see my video on adjoint functors. So the point here is that whenever we have adjoint functors, we have a monad. All right, so if we start at this category D, and then we go along this functor L, and then we compose that with this functor R, well, we have an endofunctor of D, a functor from D to D, which is the functor R after L. And if I say that is equal to T, well, perhaps you see where I'm going with this. It turns out that this functor R after L in this case is basically going to give us a monad. All right. So let's remember from the beginning this sort of picture here, which is describing what a monad is. So what do we need to get a monad? We need a endofunctor T, and we need these two natural transformations, eta and mu. So when we have adjoint functors, as described by this sort of diagram here, how do we get our ingredients for our monad? This is what we want. We want to take an adjunction and get a monad. And we can always do it. Here's how we do it. Our endofunctor T is going to be this functor R after L. And our unit for our monad, eta, is simply the unit that we have for our adjunction. Remember, this unit here is a natural transformation from the identity arrow of D to R after L, which is T. So it already has the proper form, and indeed it's what we want to be the kind of unit of our monad here. And so finally, how do we get this multiplication natural transformation mu here? Well, we can do that too. Okay, so if we think about what is T after T, well, we know T is R after L. So T after T is just R after L after R after L. And then if we do this kind of, and then if we form this sort of horizontal composition of natural transformations, then we've got this co-unit epsilon here in the middle. That's going to change L after R to identity of C. And so if we form this horizontal composition of natural transformations, that's going to be a natural transformation which goes from R after L after R after L to R after L. Or in other words, it goes from T after T to T. And this is exactly what we want to be mu. Okay? So there we have it. When we pick T to be R after L, when we use our old unit, and when we pick this to be mu, then this data here actually gives us a monad. So this, I think, is a very beautiful thing because it means that wherever we have our joint functors, we have monads, and then we can cook up things like Clysley categories. We can do lots of very cool stuff. But what's even more interesting, I think, is that this kind of, but what's even more interesting, I think, is that we can also go the other way around as well. Whenever we have monads, we have adjoint functors. Okay, in fact, usually when we have a monad, we can find at least two different pairs of adjoint functors associated with that monad. And so we're sort of able to infiltrate the social network of monads and adjunctions and find all of these very interesting characters that are very useful to us throughout our category theoretic explorations. Okay, so now I want to talk about some adjunctions which arise when we have monads. So I'll just quickly remind you that this kind of condition here is a kind of equivalent way of saying that we have an adjunction. Okay, when we have the functor R going in the opposite direction to the functor L, we have this kind of isomorphism here, which is natural in X and Y. So here, of course, C of A comma B represents the set of arrows from A to B. So we're talking about Hom functors here. Right, so now let's suppose that we have a monad T on this category C. Okay, so we have T, we have its unit, and we have the multiplication. And so given that information, we already know how to construct the Clysley category of T. We saw how to do that at the beginning. And it turns out that there's actually adjoint functors between the category C and this Clysley category of T. So now let's briefly talk about those functors. So firstly, what about this functor L? Well, this is sometimes called the Clysley inclusion. Okay, so think about the maybe monad case that we started with. You know, the idea that we can think of a total function, a function that's defined for all of its inputs. We can think about it as a sort of special case of a partial function. And in that sense, we can sort of inject the category C into the Clysley category of T. And that's sort of what this functor L involved in this adjunction is doing. So more precisely, if we have an arrow K from X to Y, then L is going to send that to the Clysley arrow from X to Y. Which Clysley arrow from X to Y? Well, the one that corresponds to the ordinary arrow, which has this kind of form. It goes, we start at X, we do K, we get to Y, and then we use our unit to get to T of Y. So doing this functor L here on this arrow K makes this arrow here, which is really kind of like an arrow that's similar to K, but in this Clysley category. So that's this functor L. What about this functor R? What about the right adjoint to our functor L? How is that defined? Well, let's take an arrow. Well, let's now take an arrow in our Clysley category. So we'll take an arrow V from X to Y. Now that's a Clysley arrow. So it's going to correspond to an ordinary C arrow, which goes from V to T of Y. Now, what's the image of this Clysley arrow under our right adjoint functor R here? Well, it turns out as a result, we're going to get the arrow of C, which starts at Tx, and then we do Tv, and we get Tty, and then we do mu, and now we get Ty. And so we see that this functor R here changes this arrow V from X to Y to this arrow here from Tx to Ty. But this arrow V was in the Clysley category, and this arrow here is back in the original category C. And so I claim that this functor R is the right adjoint to this functor L. And so since we have these adjoint functors, we ought to be able to produce the unit and the co-unit involved. It turns out actually that the unit is just going to be the unit for our monad. But instead of giving you the co-unit, I'll give you this kind of equivalent information, which is the nature of this kind of natural isomorphism between these Hom sets here. And so on the left, what we have is an arrow from L of X to Y in the Clysley category. So we know that L doesn't actually change objects. So L of X equals X. So this is just a Clysley arrow from X to Y. So let's say F. And we want this to correspond to an arrow from X to R of Y. And we know the way that R works on objects. It sends this object Y to T of Y. So this is just going to correspond with an arrow from X to T of Y. And that's actually just going to be, and so how do we put Clysley arrows from X to Y into correspondence with ordinary arrows from X to T of Y? Well, that just happens directly from the definition of a Clysley category. Okay, that's how we started by defining what a Clysley category is. We said that a Clysley arrow from X to Y corresponds to an ordinary arrow from X to T of Y. And it's that correspondence which is precisely this kind of adjunction, which is allowing us to kind of go between these two different kinds of arrows. And so if you watch my video on adjoint functors, you'll see that, if you understand how this kind of isomorphism of Hom sets works, you can figure out all the rest of the stuff that's going on within the adjunction here. Okay, so when we have a monad then, we always have these kind of adjoint functors between our original category C and this Clysley category. But we have something else as well. There's another category, and we have an adjunction involving that and C as well. And so the other category is called the Eilenberg-Moore category of the monad. And so to introduce that, I want to talk first about algebras. So an algebra is a very kind of simple idea, which is very powerful. It's surprising, actually, I haven't got onto it yet in this category theory for beginners course. I suppose that's just a consequence of how many interesting ideas there are in category theory. But here's the idea. So if we have a category C and we have a endo functor F, so just a functor F from C to C, then what we call an algebra of F is just an object X of our category C together with an arrow A from F of X to X. Okay, so it's really a very simple kind of idea. An algebra of F is just an object of X and an arrow from f of x to x. Right, so that's the idea of an ordinary algebra, of an endo functor. And in fact, these algebras can be thought of as objects within a category. We call that category alg of f. And so its objects are these algebras of f. And what's a morphism, what's an arrow, h, from one algebra to another algebra? Well, it's going to correspond to an arrow h from x to y within our original category C. But that arrow h has to make this kind of diagram commute. Okay, so if we go along the arrow A and then we go along h, we get the same result as if we go along f of h and then we go along B. That's what constitutes a morphism h from this algebra XA to this algebra YB. So there we are. We know what the objects are. We know what the arrows are. And so we now understand this category alg of f. And it's amazing, again, that there's a whole category like this for every single endo functor. But anyway, I want to get to this idea of the Eilenberg-Moore category. So there's another notion, and I must say I find this terminology a little confusing, of what's called an algebra over a monad, also known as a module over a monad. And so the idea of an algebra over a monad is really very similar to this idea of an ordinary algebra. It's just that we have an extra constraint. Okay, so when we have a monad T with its multiplication and its unit, and when we talk about an algebra over a monad, we're talking about a similar kind of structure. Okay, so an algebra over a monad, again, consists of an object x and an arrow A from T of x to x. So it's basically the same kind of thing as an ordinary algebra. However, when we're talking about an algebra over a monad, we insist that this kind of structure plays especially well with our kind of monad structure, in the sense that these two diagrams have to commute. Okay, so of course when we have a monad, we have an endo functor, and so an algebra over a monad is this normal kind of structure of an algebra. But when we're talking about algebras over monads, we require that these two diagrams have to commute. And so now we know these definitions. We can now define the Eilenberg-Moore category for this monad T. Okay, so we call this category EM of T, and it's just the full subcategory of alg of T on the algebras over the monad T. Okay, so basically we look at all of the algebras of T, and we look at the category of algebras of T, and these are sort of algebras with no special constraints, and we've got these kind of morphisms between those algebras, and then we restrict ourselves to only look at the kind of objects which correspond to these sort of proper algebras over this monad T, the ones that make these kind of diagrams commute. And we take all of the kind of arrows that were in alg T between such objects, and together that kind of structure gives us this Eilenberg-Moore category of T. So once we've got that category, we have yet more adjoint functors. And so here we go. Again, we have, and so here we go. So let me remind you of the setting here. Basically, we're starting with this category C. We're starting with this monad T with its unit and its multiplication. And we're interested in cooking up adjoint functors. We've already talked about how to do this involving the Clysley category, but it turns out we can also do this involving the Eilenberg-Moore category. Okay, so now we know what the Eilenberg-Moore category is. What we want to do is describe this left adjoint and this right adjoint here. And so the way that this functor going to the right works is actually pretty simple. In fact, this is really what we might call a forgetful functor. Okay, so if we take so if we think about an arrow in the Eilenberg-Moore category, maybe we have a morphism H from the algebra x comma a to the algebra y comma b. Well, if we do this r dash functor on this arrow, we end up with an arrow of the category C, and that's just going to be the original arrow H from x to y here. So this functor r dash is really just a forgetful functor which takes an algebra and then it forgets about this fancy structure and just gives us the sort of underlying object. Now what about going the other way around? What about doing L dash? This is the left adjoint to R. So this is actually going to be a free functor. So this is much more interesting in a sense. So the way that this one works is that if we start with an arrow F from x to y in our category C, and we do L dash on that kind of arrow, that's going to give us an arrow of Eilenberg-Moore category. And so how does this free functor L dash work? Well, it's going to send x. Well, it's going to send x to the algebra tx comma mu x, and it's going to send y to the algebra ty comma mu y, and this arrow f is going to get lifted under L to become the arrow tf. And so there we have it. We've described this forgetful functor r dash and the left adjoint, the free functor L dash. And the unit involved in this adjunction is just the unit of our monad. And it turns out that the co-unit is described like this. Okay, so if we have an object like x comma a in the Eilenberg-Moore category, then the kind of component of that, then the kind of component of our co-unit for that kind of object is just this arrow a itself. And so I thought I'd at least say something about why these kind of algebras over monads are important, because they are really important. And I thought a good thing to look at is the idea of a category itself, because I think this is a really interesting kind of connection here. So you may know that there's a deep connection between graphs and categories. So we have this category of categories, which we call cat, and we have this category of graphs, which I write like this, because it's really the category of functors from this diagram here into set. But we could equally call this category something like GRPH. It has objects as directed graphs and arrows as graph homeomorphisms. Now it's well known that we have these adjoint functors between cat and the category of graphs. And so if we have a category, like let's say this one here, and we do this forgetful functor u on it, we just get the kind of underlying graph of that category. So the objects of our original category become vertices, and the arrows of our category become directed edges. That's all that u does. It just forgets the kind of compositional structure. But there's a left adjoint to this forgetful functor u, and that's this free functor f, which is kind of much more exciting in a way. If we operate f on a graph, for example this one here, we get a category. Now the objects of that category are the same as the objects of our the same as the vertices of our graph, and then the arrows of this category correspond to all of the kind of walks or composable strings of arrow or composable strings of directed edges that we can form in our original graph. Okay, so we have these length 0 walks which correspond to identity arrows, and also going along this edge forms a walk. Or we could go along both of the edges, or we could go along this edge, that's a walk, or we could go along both edges, and that's a walk. And we can compose these walks, and so each arrow now in this new category we formed corresponds to a walk that we could do in our original graph. And then the ways that we could compose our walks in the original graph give us the notion of arrow composition in this category. So we could really call this the sort of free category generated by this kind of graph that we're operating this functor capital F on. And so I'm glossing over a lot of details, but suffice to say, this free functor f here is the left adjoint to this forgetful functor u. And so, of course, if we do this functor f, and then we do this functor u, that means we have a monad. And it's an interesting monad. So let's call that monad T. And it's interesting because this is a monad which is really defined in the world of graphs. Okay, it's a endo functor of this category of graphs. And so how can we think of this? Functor T? Well, it's going to take a graph, and then it's going to generate the sort of free category of that graph, and then it's going to again forget about the sort of this sort of compositional structure that it's just created. So a more direct way to think of T is that it's going to get the original graph and then form a new graph that has directed edges corresponding to walks in the old graph. And then this unit here of this monad, well, this is just going to embed our original graph in this kind of bigger graph of walks by sending each directed edge of the original graph to a length 1 walk in the new graph. And this mu here, this multiplication, this is just going to send the graph of walks to the graph of walks by composing walks, if that makes sense. If you find what I'm saying bewildering and you want to learn more about this, you can Google the free category of a graph, understand the adjunction, and then you can understand the adjoint functors, and then you can extract this monad from the adjoint functors as I've already described. But the key thing I want to say is that we can really look at the situation as if we're starting from this monad here. Okay? And that's because there's a sort of way of thinking about what a monad is. And that's basically the idea that a monad is a sort of algebraic theory in a sense. And in this sense, an algebra for such a monad can be thought of as a sort of model of that theory. Now, why am I saying all this? Well, why I'm saying all this is because we can actually think, and this is the sort of big reveal here, we can actually think of cat here as actually being the Eilenberg-Moore category of this functor T. Okay, so in other words, this is giving us a new view of what a category actually is. A category could actually be thought of as an algebra over this kind of monad T that I've just been describing. Now, why do I say this? Well, just to think about what an algebra over T is going to look like. It's going to correspond with a graph X and an arrow and a graph homeomorphism from T of X to X. Let's say a graph homeomorphism A. So what does this mean? Well, it means we start with a graph X, and then we form this kind of graph that has directed edges as walks on the original graph. And then we want to form this sort of morphism, which is going to be sending each of those walks to one of the original directed edges of X. And so really the way that we can think of this kind of arrow A here, this graph homeomorphism, is it's sort of like a valuation arrow, which is actually going to be defining for us the idea of composition within our category. Okay, so this really, I'm glossing over a lot of details, but what I'm really saying here is that an algebra over this kind of monad T that I've been talking about can really be thought of as defining a category by specifying which arrows compose to give which results. Now, I'm glossing over a lot of details here. In fact, if you want to look at section 2.4.2 of Eugenia Cheng and Aaron Lauder's book, High Dimensional Categories, an illustrated guidebook, you can see more details there. Okay, so since I've come this far in talking about monads, there's a couple of sort of miscellaneous remarks I want to make. One of them is another way of looking at the Clysley category. So if you recall, the Eilenberg-Moore category can kind of be thought of as a category of algebras over a monad T. And recall that there was this kind of free functor, which I'm calling L' now, which went from our category C to the Eilenberg-Moore category of our monad T. And here, L' was this left adjoint. Recall that we had this left and right adjoint between C and the Eilenberg-Moore category of T. And so if we have an object A in our original category C, then its image under this functor L', this free functor, can appropriately be called a kind of free algebra generated by A. And this is going to be one of the objects of this Eilenberg-Moore category. And so we have certain objects of this Eilenberg-Moore category which can be regarded as free algebras. And we can consider the full subcategory of the Eilenberg-Moore category on these free algebras. And let's call that category free. So this is the subcategory of the Eilenberg-Moore category of T that we get by just taking all of the objects of the Eilenberg-Moore category of T, which are images of some object in C under this functor L', and taking all the arrows between such objects. So that's our category free, which is this category of free algebras from this monad T. And now it turns out that that category of free algebras that I'm calling free here, it turns out that that's actually just equivalent to the Clysley category of T. So this is another way of thinking about what the Clysley category of T is. And it's an interesting kind of alternative perspective. Okay, so one of the wonderful things about monads is that they give you back doors into lots of different subjects. And so I want to briefly mention such a sort of back door into probability theory. So there's a certain monad on set which basically allows us to think about lots of stuff to do with probability theory. And I think it's well worth mentioning. So there's actually quite a few kind of monad-based approaches to probability theory, but I want to talk about one of the simplest, which is involving something called the finitely supported distribution monad. And so if you want to find out more about this and about the things I'm about to say, I suggest having a look at section 2.1.1 of Toby Smythe's paper, Bayesian Updates Compose Optically. But anyway, what's the idea? Well, the idea is that we have a certain monad on the category set. So we have an endo functor T, and we have our unit eta and our multiplication mu. So I will tell you how these things are defined. So firstly, let me tell you about the idea of a probability distribution on a set A. So the idea here is that a probability distribution on a set A is a function from A to the unit interval that has the property that if we add up all the values of the function, we get 1. And we're interested in finitely supported probability distributions. So if we have a probability distribution P, then we define the support of P to be the set of elements of A which get sent to non-zero values by P. So if you like, it's the set of elements of A associated with positive probabilities. That's what we call the support of the probability distribution P. And so what we're going to do now, we're going to make this functor T, and the way it works is that it sends a set A to the set of finitely supported probability distributions on A. And a finitely supported probability distribution is just a probability distribution, as in a normalized map from P to the unit interval, which has finite support. So if we look at the support of such a probability distribution P, it should be finite. So in other words, T of A here, we can think of it explicitly as the set of maps to the unit interval that have all their values adding up to 1 and that are only non-zero for finitely many values. So that's what T of A is. It's the set of finitely supported probability distributions on A. So now we know how this functor T works on the objects of sets like A. How does it work on arrows? Well, if we have an arrow of sets, that would be a function f from a set A to a set B. And that gets lifted to be this function T of f, which sends finitely supported probability distributions on A to finitely supported probability distributions on B. And the way it works is it just sort of pushes forwards a probability distribution on A along F. So to be more explicit, if the input here is this probability distribution P on A, then the result of doing T of F on P is going to be this probability distribution P dash. And that's going to associate an element little b with this probability, which is obtained by adding over the values little a, which get mapped to b under F, of the probabilities of those values under the original probability distribution P. Okay, so that's how this functor capital T works. So now I just need to tell you how eta and mu work. Now the way that eta works is pretty simple. So we want something that sends an element of A to a finitely supported probability distribution on A. And we just send an element A to the delta distribution on A. So that's the probability distribution where elements equal to A get a probability 1 and other elements get probability 0. Describing mu is a little bit more involved. So the way this mu works, so if I keep saying finitely supported all the time, it's going to get confusing. So just take it for granted that all the probability distributions I'm going to discuss are finitely supported. And so mu here, it's going to send a probability distribution over probability distributions to a probability distribution. So how does this work? Well, let's take an example element here of T of A. So we'll call this script TP. So script TP is a probability distribution over probability distributions. So script TP sends every probability distribution, as in every element of T of A, to a probability. And mu of A is going to map scripty P here to some probability distribution over A. And so in particular, mu of A is going to send scripty P to this probability distribution P star over A. And how is P star determined? Well, P star is going to associate an element little a with the probability obtained by adding over all of the probability distributions chi over A of the probability distribution of the probability that chi occurs under scripty P times the probability that little a occurs under chi. So basically, the way that mu works is it takes a probability distribution over probability distributions, and then say you're interested in what the chance of a certain result little a is of coming up. Well, you just add over all the probability distributions of the probability of that probability distribution coming up times the probability that little a comes up under such a probability distribution. It sounds complicated, but the Clysley category that you get out when you consider this monad T is very, very cool and really quite simple. So set is a great place for doing functional programming, right? We have these objects as sets and arrows as functions, and we can think about how to compose the functions and so on. But the Clysley category of this finitely supported distribution monad is really a sort of category of stochastic maps. Okay, so it again has arrows as, it again has objects as sets, but now the arrows, rather than being functions, now the arrows are stochastic maps. They're sending elements of the source set to probability distributions, finitely supported probability distributions over the target set. So this is really kind of like a, if you think about this computationally, it's kind of like a generalization of the ordinary kind of functional programming where you can work with things that are probabilistic, which I think is very, very cool. And the people who are into probabilistic programming really like this kind of monad-based approach in many cases. So let's think a little bit about the Clysley category of this monad T. What's it look like? Well, as usual, an arrow F from A to B in such a Clysley category corresponds to an arrow, or in this case a function, F from A to T of B. So that means it's going to be sending elements of the set A to finitely supported probability distributions over the set B. And so here's an example. Okay, so here, if we have an input of 1, we get X with a probability 1. If we have an input of 2, we get X with probability 0.3 and Y with probability 0.7. If we have an input of 3, we get X with probability 0.5 and Y with probability 0.5. And so we can sort of, well, we could represent what's going on here with a kind of matrix. So you can think that each of the elements of the input is getting sent to a sort of vector of probabilities over the outputs that add up to 1. And so we can kind of clip together these three vectors that we get for the different inputs to represent this stochastic map F by a matrix. We can also use this kind of notation that looks kind of like the notation of conditional probability. So we can say, well, we can record things like the probability that we get an X as our output when 2 is our input, and we're using this stochastic map F. And in that case, we see that F is sending 2 to this probability distribution like this. And so the probability that we get an output of X when the input is 2 equals 0.3. And of course, we have a way of composing the arrows in this Clysley category. And you can look at the theory we've already described to ascertain how composition works, but it's quite kind of intuitive. Basically, if we want to compose these Clysley arrows, so we want to do G after F, well, it turns out that basically we can just think of this in terms of matrix multiplication. So this is the key formula. And this is actually something well known from probability theory. It's something called the Chapman-Kolmogorov formula. And it's basically just multiplication of matrices. But to think of it more explicitly, what this formula is saying is that under the composition of the stochastic maps G and F, the probability that we get an output of little c when the input is little a can be obtained by adding over all of the possible intermediary values little b of the probability of getting b given a using f times the probability that that intermediate value b yields little c under the stochastic map G. So it's quite self-explanatory, really. We just add over all the possible kind of intermediate points that we could encounter when we're sort of composing these two stochastic maps. And so there you have it. That's like a very, very brief outline of this kind of doorway into probability theory, which is afforded by using monads. I mean, there's lots more to say. I mean, there's lots more that could be said about this. I mean, there's connections with convex spaces. There's lots of similar sorts of approaches to probability theory that use more sophisticated categories incorporating measure theory. For example, there's a category called stock and there's something called the jury monad. So if you're interested in this kind of stuff, you can Google terms like probability monad and you'll find lots more interesting theory. Anyway, something else that I want to mention kind of briefly, just because it's a really rich source of different monads. There's all different kinds of monads that you can cook up by following this recipe I'm about to give. And so I want to talk about this. This is this idea of the left action monad. Okay. So this is this idea of an action monad. So I'll just quickly give you the general definition. So in any situation where we have a monoidal category D and we have a monoid S in that monoidal category, we can always cook up a monad. And how do we do it? Well, what's the endo functor T that we're going to have? Well, it's just this functor where we do the product of S with whatever we have. So, for example, when we do this functor T on an object X, we end up getting S tensor product X. So that's the nature of our functor T. The only other things we need to know are the unit and the multiplication. And the X component of the unit is given by this diagram here. So it's what we get by doing the left unitor and then doing this arrow here where we're basically using the I from our monoid. And the multiplication arrow, we get it by, and the multiplication arrow that has components making this kind of diagram commute. So we get mu x by doing our associator isomorphism, and then by doing the operation of our monoid, sending S times S to S. And so this gives us so many ways of cooking up new monads. I mean, one example, just one tiny example, is like if you take, say, the category of smooth spaces, well, that's a topos. So it's a monoidal category. So and then there's going to be lots of monoids in there. And for every monoid, you can then cook up a monad like this. So we can find an abundance of monads for each of these monads. We can find these adjunctions, then we can find more monads, and yeah, monads are plenty. So that's pretty much all I wanted to say. I'll just say a couple of extra things. One of them is that this whole idea of monads can be generalized. Okay, so like the key kind of mantra that I've been saying in this video is like a monad is a monoid in the category of endo functors. So let's see if we can just sort of draw that quickly. So we'll think about the category cat. Okay, it has objects, which are categories. We'll pick an object, so that's our C, for example. And now we look at the endo functors of that category. So here's a functor from C to C. Here's another functor from C to C. And so these functors, these loopy arrows here, they're corresponding to, so here's the category C. This is a functor T1 from C to C. Here's another endo functor T2 from C to C. And then we have these natural transformations between these things, like this natural transformation beta here. And so what we do is we look at this category of endo functors of C, and then we find a monoid on it, and that's what we call a monad. But why can't we do this in a more general setting? I mean, what is cat but a two category? Okay, cat is a two category. Okay, cat, because cat is a two category. Okay, it has 0 cells as objects, it has 1 cells as arrows, and it has 2 cells as natural transformations. They're the arrows between the arrows. So more generally then, we could pick a 2 category, and we can pick a object of that 2 category, and then we can consider all of the And then we can consider the kind of category that has the objects as endomorphisms of that object and arrows as 2 cells between those things. And if we find a monoid on that structure, well, we could actually regard that as a monad as well. So that's a more general definition of a monad. In fact, we could say the same thing, not necessarily in just an ordinary 2 category, but in a bicategory. Now, a bicategory is basically like a 2 category, except some of the aspects of composition only work up to isomorphism in a bicategory. Anyway, I just wanted to point out that there is this sort of more general view of what a monad is, which is basically just like the kind of monads I've been talking about to do with functors and so on, except sort of generalized, so that rather than relying on the kind of 2 category structure of cat, it can be the whole idea of monads can be framed in some kind of more general 2 category or bicategory. And then the other thing to say, the usual thing, is that yes, we can dualize everything. Okay, so I've talked about a lot of concepts today, and there are duals of lots of these concepts. There's a thing called a co-monad, there's a thing called a co-monoid, there's a co-Clysley category, there's a co-Eilenberg-Moore category. And so, yeah, there's a lot of stuff to think about. So I hope you enjoy monads.